Hi, in the last video, I discussed about how do we measure the association between two quantitative variables by using the Pearson's correlation coefficient. We denote it by lowercase r, right? And also we did the hypothesis testing. So here, I'm going to talk about the Spearman's rank correlation coefficient. So when the variables are not quantitative or is not normally distributed, or when the presence of outliers give a distorted picture of the association between two random variables, the Spearman's rank correlation, which is a non-parametric test, can be used instead of Pearson's correlation coefficient. The sample rank correlation coefficient by Sperman is given by, we denote by R sub S, which is equals to 1 minus 6 times sum of the di square over n cube minus n, where d sub I is rank of xi minus rank of yi. So we need to rank the xi and yi and then you find out the difference between the ranks, okay? And n is the number of pairs. Note that the formula is called Spearman rank correlation coefficient. Okay, to apply this method, we need to rank both variables x and y separately and then find the difference between the rank. To test the hypothesis of rs is the r sub s is the test statistic, and the critical value is obtained from Spearman rank correlation coefficient table. Okay. If the absolute value of the obtained R sub S is greater than the critical value, then reject the null hypothesis and conclude that there is a rank order relationship between the variables if the population represented in the sample. Okay, so let us see one example. So rank correlation example. So in this example, you want to test whether these two variables rank 1 and rank 2 are associated or not. The following are the ranks by two different authorities for the efficiency of 7 different hypertension drugs. For alpha equals to 0.05, test whether there is a significant agreement between the authorities on which the drugs are most effective. Drug name A, B, C, D, E, F, G. There are 7 drugs, right? And there are two authorities. One ranked these drugs this way and then other authority rank the drug this way. Okay, so what you need to do is these are the rank 1 and rank 2, so you need to find out the difference between the rank. So what is that difference? 1 minus 1 is 0, 2 minus 2 is also 0, right? 4 minus 3 is 1, 3 minus 4. So we need to find out the square of the rank though. DSQ is difference square, okay? Square of the difference. 1 minus 1 is 0, square is 0. 2 minus 2 is also 0, square of 0 is 0. 4 minus 3 is 1, square of 1 is 1. 3 minus 4 is negative 1, but the square is positive 1. Similarly, 6 minus 5 is 1, square is 1. 5 minus 6 is negative 1, square is 1, and so on. So here the n is the number of pairs, right? 1, 2, 3, 4, 5, like that. N is 7, summation di square is sum of these. Square of the difference of the ranks, okay? That is 4. 1 plus 1 plus 1 plus 1 is 4. And R sub S, if you use this formula, you get R sub S is equals to 0.92. Also, for the critical value, we use the Spearman's critical value table that is given here, okay? For n equals to 7, so n equals to 7 here. So we'll be using the two-tail test because our null hypothesis here is rho sub S equals to 0 versus rho sub S not equals to 0. That is the alternative hypothesis. So it is a two-tail test. So for two-tail test with 0.05, okay, and then n equals to 7. So you go to 7 here. So that value is 0.786. You see that? The critical value is 0.786. Since the R sub S, that is the test value, R sub S is bigger than the critical value, we reject the null hypothesis, okay? So hence the agreement is significantly different because the null hypothesis was they agree. So both of the ranks, both of the authorities, they agree, have the similar ranking, or the ranks of the both authorities agree each other versus not agree each other. So we reject the null hypothesis, meaning that we do not agree. They are significantly different, okay? So if you want to do that in R has, so I'm doing first manually and then I will show you how to do from R directly. Okay, so how do I do that? Is look at this. R1 is the rank 1, 1, 2, 4, 3 like that. Okay, let me run that. And R2 is 1, 2, 3, 4 like that. That is the second rank. So I put that in the table, rank 1 and rank 2 is, this is what you see, right? And then what we are doing here is we are finding the difference between the rank and then square them. So 1 minus 1 is square, that is R1 minus R2, and then square is the new column that I added, D as Q. You see that? And N is the length of R1 or length of R2 because they are equal length. Okay. Now what is the formula to find out the R sub S? Is 1 minus so this is 1 minus, right, 6 summation di square, that is the di square, sum of that, 6 times summation of that, table 2 deviation square, and then divide by NQ minus N. That's what we use, right? So what do we find out the R sub S? R sub S is 0.9285. Okay. So here from the table, N equals to 7 and alpha equals to 0.05. The critical value is 7. What we got here, that is 0.768, I think 0.786. Okay, since the R sub S, the critical, the test value is bigger than the critical value, we reject the H sub 0. If you want to do directly by using R, then this is what you use. So is that like so the type is equals to two-sided. So here it is using the p-value method here, right? So it is using the p-value method. So when you do that correlation dot test, you use exactly the same formula there. So R1 and then R2 method is the Sperman, and type is two dot sided. That's what I used. So result 2 is the name that I give for the result. So if you run this and then run that one, you get the p-value is 0.006, which is less than alpha, right? So what you say there is p is less than alpha, hence we reject H0. That's what you do. Okay, guys. So this is how we do the Sperman rank correlation analysis. But one of the things you see here is none of the rank were repeated, right? Because see, all the ranks are different from each other, right? So all these ranks are not repeated, all these ranks are not repeated because the data were not repeated. So here the rank are not repeated. But in case of the rank is repeated, how do we do that? This is another example. The following data represent the number of fishes caught and their quality with rating 1 through 10. What does that mean? So they collected 32 fishes of quality 6, 41 fishes of quality 5, 31 fishes quality 3, another block of 38 fishes with quality 3, and so on. Okay, for alpha equals 0.05, we are interested to test whether there are fewer fish of highest quality or not. Okay, meaning that if the quality is high, you see that. What is the highest quality here? The highest quality looks like 9. Is that correct? See, highest quality is 9, but there are a smaller number of fish. And then the second highest is 8, 20, and another 8, 20. You see that? The quality is repeated there, right? And the number may be repeated too. The number of fishes caught may be repeated too. So in that case, so this is the repeated rank. So in that case, you find out how many ranks are repeated, and you put the average of those ranks, right? For example, look at this. Fishes, you just put those 32, 41, 31 like that, and quality it's 6, 5, 3, 3. I'm just writing based on what it is listed here, right? Now, you see that 3 and 3 are repeated here, right? This 6 is repeated to another 6 here. Similarly, you see in the number of fishes, you see that 17 is repeated. Okay, so you see that there is a repeated. That's why, since you see that the 1 and 2, it should be ranked 1 and 2, but both of them are 3, right? So on the quality, there are the smallest quality listed here is 3, but there are 2 of them. This is 31.3 and 38.3. So instead of 1 and 2 ranking, we do 1.5 ranking for both 3. Okay. Similarly, first there are 6 repeated twice. Its rank should be 4 and 5, but since they are repeated, we did 4.5, 4.5, and so on. Okay, after you do that, you find out the ds cube, meaning the difference of the rank, and then find out the square. Okay, that is, so 10 minus 4.5 is 5.5, square is 30.25, and so on. 12 minus 3 is 9, square is 81. So you do that way. Okay, so now you use the exactly same formula there. You get 1 minus 6 times summation of ds cube, right, the di square, over n times n square minus 1, and then you get negative of 0.86. You take the absolute value of that, you get 0.86. You ignore the negative sign. Now, so next we find out the critical value for two-tailed test and alpha equals to 0.05 and n equals to 12. The critical value is 0.587. Let us look at it. 0.05, two-tailed test, 12, n equals to 12. So n equals 12 is here, right? And then 0.05 two-tailed test is the upper one, this one, right? So you see that? Alpha two-tailed test, 0.05. So 0.587. That's what you got for alpha. So for critical value. So since the test value is bigger than the critical value, you see that test value is 0.86, 0.86, and the critical value is 0.587. Since it is bigger than the critical value, we reject the null hypothesis. Hence, there are enough evidence to support that the number of fish and the quality are associated to each other. Since RS is equals to negative 8.82, we can say that there are fewer fishes of higher quality, because we got that whenever the correlation coefficient is negative, meaning that when one increase, the other will decrease, right? So we say that there are fewer fishes of highest quality. Okay, so let us see how do I do this thing in the R. Okay, so let me do that. So we have 32, 41, 38, and all those data set, all the first column are here, and all the second column, the quality, are here, right? So let me run those two, and I rank the fish and I rank the quality. Now I am going to put them into the this is I'm doing manually. Okay guys, so there is a shortcut way, I'll show you. And then so what did I do here? I just put the fish and then rank of fish, quality, rank of quality. I put those 4 of the columns. Now what I'm going to do is I'm going to find out the deviation square, right? So that is, I denoted by I assign new column name DSQ, which is R1 minus R2 square. So table 3 is that, right? You see that? Let me move it a little bit up so that you can see all of those rows there. Now what is the n? N is the length of R1 or length of R2. Now to find out the R sub S, which is 1 minus 6 summation of DI square, that is that, right? And then over NQ minus N. This is what you did. So we got negative 0.86. That's what we got, right? But when you do the absolute value, then that will be positive 0.86, right? R sub S absolute value is 0.86. And from the table, n equals 12, alpha equals to 0.05, and 2 degrees of freedom, what did we get the value? 0.588, right? 0.588. So RS is the test value is bigger than the critical value, so we reject the null hypothesis. So if you want to do directly by R, then what do you do? Let me do that two-tail. Okay, type is equals to two-tail. I'm not sure whether that makes any difference there, but let me just keep that. Type is equals to two-sided. So this is the result 3 equals to correlation test R1 and R2. R1 is that, R2 is that, right? So the ranked value. If you do that, it says cannot compute the exact p-value with ties, but it still finds that values, right? It still finds. So so you know that. Let me tell you about that. So in case of the tie, we use a slightly different method. So you may get the different critical values than what we got here on this method, but you will see the same result. Okay, so what I was trying to say here is, you see that we are rejecting the null hypothesis, right? So we are rejecting the null hypothesis here too with that tie, although it shows the some warning sign. But I'm using another method that's called Kendall method. Okay, first of all you need to install this, because it was showing the warning sign. When you do directly by R, I'm using the Kendall method that will not show any warning sign. First of all, you need to run line 119. Okay, and then let me run that library after you install that package. Result 4 equals to candle R1 R2, and result 4, that's what we got. Okay, so the p-value is 0.001633, that which is also less than alpha. Okay, although it was showing the warning here, you see that, you see the warning, it was giving the rejection result, right? So we got the same rejection result when we did manually, and we use the another techniques called the candle. I did not describe what is the candle method, which is beyond this course. Okay, so but what I listed is I used the p-value. From the candle method we got 0.001, which also provides you the rejection result. Okay, that is the end of the Sperman rank correlation method and its analysis. Okay guys, thank you.